Hi, my name is Evan Sultanik, and I'm a computer security researcher at Trail of Bits. Today's talk is separated into two acts. In the first act, I'm going to be introducing funky file formats and trying to convince you that they aren't just nifty parlor tricks, that they have severe security implications. In Act 2, I'm going to be introducing two new tools that Trail of Bits recently open sourced that can help you forensically analyze files as well as reverse engineer the parsers that process them. This is the point in the talk where the speaker is expected to introduce themselves. But you can always just look up my resume if you're really that curious. But in this case, let's talk about my resume that I submitted to Trail of Bits a few years ago when I applied. And if you were to look at this, you might have actually just glossed over the footnotes here, but they're actually relevant to the talk today because my footnotes are asking you to unzip my PDF, and it's claiming that you'll get another PDF out of it that has something to do with Git. It's also saying that you can interpret this PDF as a Nintendo Entertainment System ROM. Also, the PDF is rendering the MD5 sum of itself. So let's confirm some of these things. Sure enough, the MD5 sum is correct, and the first 7 bytes of it are not a coincidence either. The PDF is in fact a zip file that contains another PDF, but if you run the file command on the PDF, file doesn't think it's a PDF or a zip, it thinks it's an NES ROM. So let's try emulating it. As you can see, the NES ROM also prints out the MD5 sum, even though the NES ROM does not have knowledge of the entire file. So this was computed using hundreds of MD5 collisions that were calculated, each of which allows us to encode a single bit of data into the file without altering its overall MD5 sum. I recorded this at around 1 a.m. this morning, and I was completely exhausted, so you'll have to excuse my terrible gameplay. I'm not going to ruin the rest of the game for you. There's actually a significant amount of content, Easter eggs, and there's actually a whole Kaizo-style platforming section coming up. So feel free to download it if you're interested. It is in active development, not because I am looking to improve my resume or get a new job, but just because it's kind of sad, but this is my hobby. On to Act 1. Files have no intrinsic meaning. I am an editor of and frequent contributor to the offensive computer security journal PoC or GTFO. It's released roughly quarterly and is always released in hard copy first at various computer security conferences, and then shortly thereafter is released digitally. The PDF is, like my resume, always a polyglot, so it's always a zip file containing feelies related to the articles therein. But in addition to that, each issue is also some other type of format, in addition to being a PDF and a zip. So in the remainder of this part of the talk, I'm going to be giving a bunch of examples, many of which come from the polyglots that I helped contribute to in PoC or GTFO. I am not the only editor. I didn't even join the editorial board from the beginning, and there are many other people that contribute to the publication and also to the polyglots. Particularly Ange Albertini and Philippe Thuin have contributed significantly to a number of the other issues, as well as I've collaborated with them on a number of the issues. I also would like to mention that the PoC in PoC or GTFO stands for proof of concept, or alternatively, pictures of cats. I have to mention this now because the publication was named before I became involved in it, and it was also named before the significant increase in the popularity of alternative meanings for the PoC acronym. So in writing, I always like to use the letters OR to represent OR instead of a programming double bar, because in some cases the laity doesn't realize that the double bar means OR, and it can get somewhat uncomfortable if you're reading one of our publications in public. Also, now that I have the stage, I'd like to address by far the most common question we are asked, which is, it appears as if our numbering scheme is hexadecimal. Why did we go directly from issue 9 to issue 10? What happened to A through F? Well, in fact, our numbering scheme is binary coded decimal in honor of the HP Saturn architecture. I'd also like to give a quick plug to the Book of PoC or GTFO. There are 2 volumes currently in print. They are a chronological compendium of the first couple dozen articles in the issues. We are actively working on subsequent volumes. They are bound in the finest quality faux leather. They have ribbons to keep your page, gilded edges, and Bible paper. And the editorial board, publish these at a significant expense in both time and oftentimes money. We do not make any money off of this. All of the proceeds go to funding free print runs at conferences, and whatever is left over is donated to charity. So please, I encourage you to patron your favorite purveyor of fine books and purchase a copy, or if you have to, buy it off of Amazon. But I encourage you, please buy it from directly from the publisher, no starch. Now, if you happen to have a copy in front of you, please rise and open your hymnals for the recitation of PoC or GTFO, Chapter 7, Verse 6. A file has no intrinsic meaning. The meaning of a file, its type, its validity, and its contents can be different for each parser or interpreter. You may be seated. The Android operating system supports a number of different file formats to represent executables, 2 of which are APK, which is really just an extension of the zip format, and DEX. A couple of years ago, it was discovered that you could create a polyglot that was at the same time a valid APK file and a DEX file. This led to a high-severity vulnerability in Android because the Android developers never anticipated this type of polyglot when they were implementing their code signing. So what happens is the code signature is compared against one version of the file, whereas when the code signing is validated and the executable is run, the other version of the file is what's actually executed. So this leads to the ability to execute arbitrary code on Android that hasn't been properly signed. So this was actually a similar technique to what we used in an issue of PoC or GTFO that was both a valid PDF and a valid APK Android executable the year before. Can anybody tell me what's wrong here? So one thing you might notice is that the list of arguments passed to the tar command are asking to extract it, but we're not providing the Z option to tell tar that we first wanted to unzip the file. It turns out that's not actually wrong, because most modern versions of tar, and in particular GNU tar, do not in fact require you to provide the Z option. What they do is they don't look at the file name, but it will inspect the magic bytes in the beginning of the file you're asking to extract. And if it looks like it was gzipped, tar will try and be helpful and automatically gzip it as if the Z option were there. So when I first discovered this feature, it like tripled my productivity. But it got me thinking, what if we created a file that's both a valid tarball and a valid tar.gz at the same time? Well, it turns out that is possible. And if you were to do that, it creates the opportunity to induce schizophrenia in the various implementations. Because if you take this single file that's both a valid tarball and a valid tar.gz and send it to two different implementations at the same time, one of which does the helpful trick of extracting the gzip first, but the other does not, you're going to get two completely different results that are extracted. And this has severe security implications, because if you're implementing any type of network filter, or if you're scanning, for example, email attachments looking for malware, you need to make sure that the way you are extracting files is the same way that the utilities the user is going to use are extracting the files. The majority of the remainder of the examples I'm going to be giving are related to the PDF file format. So why is PDF, in particular, polyglottable? Well, part of the reason is that it is a relatively old format. It's been around for around 3 decades, and its semantics and, more importantly, syntax were heavily influenced by its predecessor, PostScript, which is even older. But also, the standard for PDF was proprietary for a significant portion of its infancy. And even to this day, buying an official copy of the PDF specification is not cheap. And part of that is because Adobe doesn't want you to create your own implementations. They want to make it hard to write a PDF generator or parser, because they want you to license their libraries and their tools. But, of course, especially in the infancy when it was still a strictly proprietary format, lots of third-party vendors wanted to have their tools parse and or emit PDFs. So if you were writing a document editor and wanted to be able to export PDF, and you didn't want to go through the expense of licensing Adobe's tools or buying their documentation, you would just reverse engineer the format and keep on tweaking things until you got your document output to load in Acrobat. And if it loaded in Acrobat, then you could call it a day. And it would, it's good enough, it worked. However, what that resulted in was a lot of third-party tooling that was producing malformed PDFs that were not following the specification. And Adobe had to live with this, because if suddenly they made Adobe Acrobat more stringent and strict about following the specification, there would suddenly be a large number of documents out in the wild that Acrobat would no longer read. Now, that's not necessarily Adobe's fault in the sense that Adobe didn't create those PDFs, but the users of Acrobat are going to complain to Adobe when the PDF that they have, or the file they have that has a perfectly valid .pdf extension from their perspective, is no longer loading in Acrobat, then they're going to get angry with Adobe. So Adobe had to make Acrobat resilient to all sorts of different malformations that in an ideal world it shouldn't have had to. And moreover, all of the other PDF implementations since, PDFium, MooPDF, Poplar, XPDF, Apple Preview, all of these PDF viewers have necessarily become incredibly resilient to all sorts of malformations just by virtue of the fact that there are so many PDFs in the wild that don't conform to the spec in various ways. The issue is each of these PDF implementations handles malformations in different ways. And many times when you have a malformed PDF, there is ambiguity as to how you should resolve the malformation. And different PDF viewers resolve the ambiguity in different ways. Other reasons why the PDF file format is particularly polyglottable is that most viewers, and with some very small caveats, will completely ignore anything before the PDF header. So you can put arbitrary bytes before the start of the PDF, and most PDF viewers will not even give you a warning. They'll just render the PDF. Similarly, you can add extra bytes at the end of the PDF and it will ignore it. So neither does the PDF need to start at byte offset 0, nor does it need to end at the end of the PDF in practice. So one fun trick you can do is just take two PDFs and create a new file that is just the concatenation of one after the other. And try loading that in different PDF viewers. Most PDF viewers will render it just fine, but some PDF viewers will render the first, other PDF viewers will render the second PDF. And almost no PDF viewers will give you a significant warning. In fact, some will actually try and be nice and repair the PDF, and when you close the viewer, it will say, hey, would you like to save the PDF, even though to your knowledge, you didn't make any changes to it. The PDF file format also allows arbitrary binary blobs to be embedded inside of it. So in a sense, it's like a container format. And you can use this for steganography to store basically whatever you want inside a PDF that doesn't necessarily even need to contribute to the rendering. Alice sends an email to Bob saying, hey, I've been trying to get my resume to so-and-so in human resources, but we've had some problems with email. Could you just please print it out and give it to them? Thanks. So Bob opens Alice's attachment. It is a PostScript file, and it renders, and it looks like her resume. But little does Bob know that, well, first of all, antivirus typically doesn't scan for MIPS firmware. And this is relevant because when Bob sends that PostScript file to the printer, the PostScript contains embedded printer job language that contains a firmware image that gets overwritten on the printer. So suddenly Alice has control of the printer and can then pivot to the corporate LAN. So this has been an attack vector that's been known for a number of years. However, the issue is that people don't really use PostScript very much anymore, right? So that might be a red flag when Bob is opening. He might not even have a program on his computer that can render PostScript anymore. So that got me thinking, what if you could produce a polyglot, a single file that is both a valid PDF and a valid PostScript script at the same time? So then, on Bob's computer, when he loads the file, it looks like a standard PDF and it renders one way. But then when he sends the file to the printer, The printer interprets it as a PostScript file, and it prints something completely different. There are a number of implications for this. Like, you can imagine a contract where the PostScript version is almost exactly the same, but a few significant words are changed. So you review the contract on your computer, you print it out, you sign it, but it's actually different than what you had read previously on screen. So it turns out this is possible, and I created a proof of concept in PoC GTFO 13. So the issue, if you interpret it as a PostScript file, for example, if you load it in the Ghost View program, the PostScript interpretation is the continuation of an article I wrote in the issue describing how I did this. So if you're curious, you can download PoC GTFO 13 and read all about it. But in addition to the continuation of the article, I wanted to demonstrate how PostScript is a fully fledged Turing-complete programming language. So the following page is a programmatically generated random maze. So every time you render the PostScript, a different maze is generated. And actually, if you send the PostScript to your printer, the little microprocessor in your printer is going to interpret the PostScript code and programmatically generate a different maze every single time you print the file. And of course, the final page of the PostScript interpretation of the polyglot prints out your Etsy password, just for good measure. So kids, always remember to load your PostScript in a VM. By this point, I hope you won't be surprised that a PDF can also be a valid Ruby script. That when you interpret the PDF using Ruby, it starts a web server, and if you navigate to that web server, it serves a copy of or representation of the title page, and also the Ruby script loads itself into memory. And remember, since all of our PDFs we are creating as zips also to store our feelies, the Ruby script unzips itself in memory and also serves up all of the feelies inside of the zip. Moreover, if you click on this link, the Ruby script will serve a copy of itself. So this is a nifty little way of having our publication self-replicate. But wait, there's more. If you rename the file as a HTML file and then open it in your favorite web browser, it is also a valid HTML file. So there's no web server serving this. It is just raw HTML. Now there is some junk. This isn't valid HTML. If you were to validate it using, like an HTML validator that people used to put those little badges on their websites for, it would fail. However, using some JavaScript, we can clean up the DOM and make everything look pretty again, to the extent that you wouldn't even notice that anything was wrong. So this is an HTML page that's also a PDF, that's also a zip, that's also a Ruby script, that's also an HTTP client. You probably have never seen this building before, but it's a really interesting place. It was in active use for 65 years and was only recently decommissioned. For most of its lifetime, if not all of its lifetime, it was the largest building in the world by some metric or another. I'm not exactly sure which, but it was a huge place. It had like over 3 million square feet. And to put that in perspective, the Tesla Gigafactory is about half the size of this building. It's so large that the roofers that are tasked with maintaining the roof have to restart from scratch every time they get to the other end. The roof is so large. Moreover, those roofers need to have the highest clearance issued by the Department of Energy, because this is, in fact, a Department of Energy site. And moreover, this is where, for those 65 years, the US government built, maintained, upgraded, and decommissioned its nuclear arsenal. So what does this have to do with documents? Well, the building, which, by the way, is called the Kansas City plant, was tasked with this impossible problem because, at best, the creators of these devices are retired, and at worst, they're dead. So how do you know what to do when you're cracking one of these things open and trying to figure out how to upgrade it, right? Capacitors don't last forever. Electronics and computers get upgraded. How do you know how to modify, update, and integrate with all of this old technology? This requires some sort of engineering preservation. How do you record something such that generations ahead will be able to understand and distill the engineering knowledge that went into creating it? Now, nuclear devices are a bit of an extreme example, but you've probably experienced this in your own lifetime. Like, for example, if you've ever tried to open a Word 97 document in a more modern version of Word, chances are it didn't look exactly the same as it did before. Line breaks probably aren't going to be exactly where they were before. Font sizes may be slightly different. Image sizes may be different. Tables may be misaligned, and so on and so forth. And what happened if you wrote all of your documents in Lotus Word Pro? Would you be able to open them now? Chances are it would be pretty difficult. And that's only 20 years ago. 65 years in the future, are you going to be able to, or are your children or your grandchildren going to be able to open the files that you're writing today? Are they going to be able to see the pictures you have on your hard drive? See all of the documents you're writing? This is a real problem of preservation and archival. And so this was joint work. I had the privilege of doing some work with the Kansas City plant and the DOE. This is joint work with Dr. Bill Regley. But Anshul Bertini, who we saw earlier with the Bible, he's a collaborator of mine and also co-editor on PoC or GTFO. And he's really the master of many of these polyglots and funky file tricks. This is in large part what motivates him, and I encourage you to go on YouTube and look up some of his presentations on this subject. But it got me thinking, what is the file format that, at least today, we use to preserve the things that we create, at least in the technical realm? And that, of course, is Git. But you might say to me, well, Git isn't a file format. It has this whole directory structure and database and so on and so forth. Well, I wasn't aware of this until I dug into it, but apparently there is a command called git bundle. And it's not nearly as well known as it should be. The git bundle command can take an entire Git repo or a subset of a repo and bundle it into a single file. And the intention behind this is to be able to take that file, sneaker net it across an air gap, and then you can actually run the git clone command on that file, and it will clone a repo as if you were cloning from a URL or a path. Since PDFs, as we learned before, don't really care what happens before the byte offset 0, before their header, and they ignore stuff that happens after their trailer, As long as the PDF exists in this bundle file format uncompressed, then most PDF viewers will just display it, ignoring everything else in the bundle file format. I'm glossing over some details here because there are some caveats with like deflate encoding, which I have workarounds for. But ultimately, if you go into the Git source code, which thankfully was written in strict adherence to the Unix philosophy of making everything really atomic, the git bundle command delegates by actually making a syscall to the git pack objects command, which is what's called git plumbing. So you've probably never heard of that command, but that's also the command that's used to update like the database whenever you do a pull or a push. So all you need to do is add a file argument, or add a command line argument to the pack objects command to tell it not to compress anything, and you'll get a bundle that has the PDF in an uncompressed state, and it will be a valid PDF. So I have a patched version of Git that does this. On my GitHub page, it also has a number of other enhancements to make things a little bit easier for you. But ultimately, if you use this patched version of Git to make a bundle, and you have a PDF committed inside of your Git repo, then the bundle will be that PDF. And any vanilla unpatched version of Git will be able to clone from it. So what you end up with is, here I have an article describing how I did this. That article is a Git bundle, a Git repo, that if you clone, contains the LaTeX source code for itself and also a copy of itself. So I hope by this point I've convinced you that files have no intrinsic meaning. These types of funky files are not just nifty parlor tricks, but actually have severe security implications and also digital preservation implications. So what do we do about it? And that brings us to Act 2. Introducing two new tools, PolyFile and PolyTracker. Internally at Trail of Bits, we call the project that has produced these tools Automatic Lexical Annotation and Navigation of Parsers. This is a backronym created solely for the purpose of referring to the project as the Allen Parsers project. So what are the goals of the project? First of all, we want to create a semantic map of the functions in a parser. We have some parser and we don't understand how it's implemented, or we don't understand what it's doing under the hood. Was it created from a parser generator? Is it a shotgun parser? Was it created by hand? How does it work? So we take a file, and what we want to be able to do is send that to the parser and then somehow divine what portions of the file are operated on by what portions of the parser. So you have all these functions in the parser. What are they doing? Is this first function responsible for parsing a certain part of the file format or doing a certain type of lexical processing? And the reason why we want to do that is our ultimate goal is to automatically extract a minimal grammar specifying the files accepted by a parser. So the reason why we want to do that is that our underlying hypothesis is that the majority of the potential for maliciousness and schizophrenia and ambiguity within a parser will exist in the symmetric difference of the grammars accepted by all of the different implementations of the file format. In other words, if there is some ambiguity in a file format specification or some potential for malice, not all of the implementations of the standard are going to exhibit that malice in the same way. If there is some bug that can cause a problem with Acrobat, chances are that same bug is not going to cause a problem in Foxit and macOS Preview and MooPDF all at the same time. So if you take the lowest common denominator of the grammars for all of those parsers and take the union of them, that will generate a safer subset of the file format. And that's also ultimately the goal of the program that is funding a lot of this work, the DARPA SafeDocs program by Dr. Sergey Brados. And the goal of that program is to create safer, formally verified parsers, but also to create and automatically identify safer subsets of file formats. For example, by removing ambiguity in the file specification, having rigorous grammars, and also removing unnecessary features from the format. There's a significant amount of related work to what we are trying to do, both in the realm of trying to get ground truth of what the file format is and what the semantic mapping or the semantic layout of an individual file is, but also in instrumenting a parser to try and get all this information out of it. Ange Albertini has an excellent project called SBUD that has a number of different complementary tools for doing visualizations and forensics on various file formats. However, it is currently limited by only having support for a number of image file formats. Our tools, although do integrate with SBUD and emit a file format that can be ingested by SBUD. The Kaitai Struct project is a very popular project that has a domain-specific language for specifying file formats, particularly binary file formats, and also has a multi-language parser generator for the specifications. And more importantly, they have a library of many specifications of file formats in their grammar format. The problem with Kaitai Struct is that it's difficult to specify context-sensitive languages, and specifically like textual. It wasn't really designed to work with textual formats like XML, HTML, or PDF. So to my knowledge, there are no extant specifications that allow you to parse those using Kaitai Struct. In the realm of parser instrumentation, there are both dynamic and static instrumentation techniques. In the realm of dynamic techniques, one of the most promising is called taint grind, which is built on top of val grind. The issue with taint grind is that we found it to be intractably slow. So a PDF parser that would normally take milliseconds to execute, we gave it hours, and it still didn't terminate. You may be familiar with the AFL Analyze tool, which is built on top of the AFL fuzzer. And in many ways, what we're trying to do is similar to that, but in fact, the dual of AFL Analyze. So AFL Analyze takes a parser and tries to reverse engineer the file format, whereas what we are trying to do is take a known file format and reverse engineer how different parsers operate on it. The LLVM data flow sanitizer is a static instrumentation technique, so you can take any code representable in LLVM IR, so for example, compiled down using Clang or Clang++, and the data flow sanitizer will automatically instrument the code at compile time such that you can track taint flow through the program relatively efficiently compared to like taint grind at runtime. However, there are severe limitations on the number of taints that you can track at one time, which effectively makes it only feasible for tracking like a handful of bytes from the input file. So you can't really do universal taint tracking, or you can't track all of the bytes from a reasonably sized PDF. So our approach for doing the semantic labeling of file formats to get ground truth is that first we do polyglot-aware file identification. We want to have a technique that will work kind of like the Linux file command, but instead of stopping at the first match that it finds, to try all the different file formats and return multiple if, for example, the file is a polyglot. Plus, to also try every single byte offset in the file, because not all file formats, as we've seen, have to start at byte offset 0. And then for a subset of those formats that we have resilient parsers for, so if we identify that, oh, it looks like a PDF is starting at byte offset 10, let's take our PDF parser that's been instrumented to keep track of initial byte offsets and parse the PDF and emit an AST that has been annotated with all of the lexical information that we retained from the parsing process. So in other words, we want to end up with a hierarchical labeling where each byte in the file can be mapped back to one or more semantic labels for what that byte represents, and have byte ranges for all of the different objects within the different file formats. Then we want to instrument the parsers statically to keep track of what bytes of input the parser is operating where. So this will give us insight into the types of data structures the parser is using, the control flow of the parser with respect to the semantic labeling of the file, and so on and so forth. So we draw a lot of inspiration from the LLVM data flow sanitizer, and we've implemented this as an LLVM IR pass. So any code that can be compiled down to LLVM, so basically anything that's in C, C++, plus any other language that has an LLVM front end, or a black box binary that has been lifted to LLVM IR using a tool like Mixema or Remil. So then we use a process similar to the data flow sanitizer to instrument the code. However, we use heavily modified, well, basically we stripped out the data flow sanitizer's internal representation for its taint tracking and replaced it with a data structure that makes much more reasonable trade-offs to provide universal taint tracking without the memory explosion at negligible increase in computational runtime. So an uninstrumented parser that would parse a PDF in a couple milliseconds might require half a second to parse instrumented, which is perfectly reasonable, and for a human is almost not noticeable. This approach has resulted in two tools that were recently open sourced by Trail of Bits. PolyFile, which performs the polyglot-aware file identification with a database of over 10,000 file formats to draw from, and emits a JSON file containing the hierarchical semantic mapping of the input file. And the output file format is actually in a slightly modified version of Angelo Albertini's SBUD format. PolyFile also has support for chi-tai struct file definitions. You can draw from the library of chi-tai struct grammars and be able to hierarchically, semantically label any of those file formats also. Plus, we have a hand-instrumented version of a very permissive forensic PDF parser. We've also open-sourced PolyTracker, which is the LLVM IR pass. And as I mentioned, it is heavily inspired by, but makes great improvements upon, the Dataflow sanitizer and also Angora. It has negligible CPU overhead, and it currently supports C and C++, and we are experimenting with also using it to instrument code lifted from black box binaries. You can get them right now on GitHub. The URLs are on the screen. I'll give a quick demo of the output from PolyFile, which is the semantic labeler of input files. I mentioned that the output is in JSON. That is the computer-readable output. Mostly for debugging purposes, we implemented an interactive HTML viewer. And it turned out that this was like a really useful feature for doing forensic analysis of PDFs. So we started adding some features to it. So I'll give you a quick demo of that. So here you can see this is my PDF that I ran through PolyFile. It has a regular hex viewer, but as you mouse over the different bytes in the hex, it will show you on the left-hand side in real time what is the semantic meaning in the file hierarchy of that byte. And in the case of a polyglot like this is, if you were to mouse over a byte that had different representations between like the NES ROM and the PDF, it would highlight both at the same time. Also, you may have noticed that in the NES ROM, it actually extracted the sprites in the CHR ROM and was rendering that there. Here we're inside of a PDF dictionary, and you can drill down into key value pairs. There was a PDF object that contained a stream that contained a JFIF stream that was a JPEG object that was an image that we extracted there. In the zip, you can actually map back to the compressed bytes that correspond to the different semantic labelings within the PDF inside of the zip. So it will recursively process the contents of the zip and run PolyFile on those. And for container formats like PDF, as you saw with the JFIF stream, it will also recursively label the contents of PDF objects. It was recently discovered that you can create a WebAssembly HTML polyglot. And this caused a little bit of a stir in the Ethereum community. So I'm going to give a quick example of how you can use PolyFile to detect these polyglots. So here on the command line, we're running PolyFile. We're telling it to try all offsets within a file, not just byte offset 0. Telling it the two types of file formats we want it to focus on, so it doesn't have to waste time trying other file formats. Here it's just building its internal matching data structures. And then we will see the computer-readable output, which is JSON. But also there are log messages that tell you that it found the two different file types. So then you know immediately that it is a polyglot. This is an example of the JSON output from PolyTracker. So the PolyTracker instrumentation happens at compile time, or it happens statically before you run the parser or whatever program you're instrumenting. And then every single execution of your executable, or your parser, your program, when it terminates, or optionally you can have it emit this at some regular interval, it will create a JSON file in your current directory containing all of the functions that were executed during the parsing run or during your program execution, as well as the byte offsets of the input file that the function operated on. Or more importantly, the byte offsets of the input file that affected the control flow within that function. So then we can merge the output of PolyTracker with the semantic labeling that we got from PolyFile to be able to get a map of what those functions in the parser are actually doing. Now in this case, we have symbol names for the functions, but that won't always be the case, particularly if we are operating on a black box binary. So if we have a function that we see from PolyFile is always operating on bytes that are, for example, in the PDF xref table, then we can reasonably assume that that function's purpose is probably to parse the xref table. So we can use the ground truth from PolyFile to get semantic meaning and semantic understanding for the different functions within the parser. So why should you care? Well, you might be doing forensics on some curious file and you want to understand, is it malicious? And maybe you know it's malicious and you want to understand why or how it was constructed that way. Maybe you're looking for data exfiltration through steganography. As you saw in my resume, it was very quick and easy to see all of the embedded objects within a PDF. You can also see all of the white space, all of the empty space within a file. With PolyTracker, you can see bytes that exist within the file but are not operated on by any function. Essentially dead bytes within the file. That's a ripe opportunity for data exfiltration and steganography. You can investigate how these funky file formats are created and how we do all of these neat polyglot tricks. You may have a bug in your program and you want to get a better idea through instrumentation of what bytes in the input file are actually exercising that bug. Maybe you are writing a fuzzer and want to have intelligent malformations for a file format. That's something that we are actively working on PolyFile to be able to do. So the idea being that you take a known correct file, run it through a instrumented parser, then mutate the file in a known way or add a known malformation, run it through a parser again, and then do a diff of those two executions to see how the parser changed its behavior with respect to that mutation in the input file. You can also do this using symbolic execution to have a better understanding of the nature of how those changes affect the execution. So you can use both of our tools to help you in any of these tasks. So anytime you have code that you don't necessarily trust, operating on files that you don't trust or that you didn't create, you can use our tools to shed light on what they are doing. I'd like to acknowledge a number of people, primarily whom I collaborated with on PoC or GTFO to produce a number of the examples in Act 1 of this talk. But more importantly, I want to acknowledge Carson Harmon and Brad Larson, who are my collaborators at Trail of Bits on the SafeDocs project, and who are my co-developers of these two tools. So feel free to reach out to any of us. If you have questions, please clone the tools from GitHub. They're free, open source. PRs are welcomed, and play around with them. Let us know what cool things you're able to do or what cool new features you'd like us to add. Thanks.